For this differential equation, let's think about what's different than the previous ones. Okay, you see that it's still linear, homogeneous, but the difference is that instead of the coefficients being just numbers, I see this one x, right? Actually, this single x is going to change everything. In fact, what happens is that if you put that into some mathematical solvers like Wolfram Alpha and ask what the answer is, it will start spitting out answers that you've never seen. So the solution to this differential equation involves functions that cannot be expressed by exponential functions, sine x or cosine x, any kind of trig functions, you name it, square roots, other types of radicals or rational functions. None of the functions that we know of will be able to represent the solution of this correctly. So what happens is that people, because they still need to solve such a thing, and you might wonder, like, when would we ever get to solve a question like this? Well, you end up with non-constant coefficient linear differential equations when you try to solve things like heat equations or wave equations in 2 dimensions or 3 dimensions. When you try to solve them, you can kind of come up with some symmetry assumptions, especially when the equation, the given initial conditions are like symmetric in a circular fashion or a spherical way, then you end up with this additional assumption that you pose, which makes the differential equation to be split into simpler ones, and the simple one-dimensional differential equation happens to be something like, not this one, but other types of a second order with different x's in here. So they do appear, and because they're so the resulting equations or the resulting functions you obtain as solutions are so important, people give various names. So these are functions like the Hankel functions, Airy functions, Legendre functions, Bessel functions, hypergeometric functions. There are many, many functions that you've never seen that has names, and these are all called special functions. Okay? Now, however, for us, here's the problem. We have no idea what these functions are, not even their properties. So the question would be like, what does it mean to know the solution? Okay? And for us, the easiest way to get access to the solutions themselves is to represent the solution in terms of the power series. Okay? And that's what brings us to review of the power series. So let's for a moment review the power series. So can you tell me the power series representation, or the Taylor series, or it's also called MacLaurin series? What's the MacLaurin series representation of e to the x? Does anyone here remember the Taylor series representation of e to the x? Anyone? Okay, I'll give you the first one plus. What's the next one?
Plus x dx.
Okay, no. It's just x plus. Yes?
Isn't like 1 over n factorial?
Yes,
in there
yes, that's
somewhere?
correct. Right, yeah. It's the next one is 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth, and it goes on and on and on. Okay. It's an infinite series. Okay. Does anyone remember the Taylor series for sine of x? Anyone? Okay, let me put the very first one, x, and then what? Minus, take a guess. No one? All right. Next.
Minus 1 over 5
Plus,
factorial x.
plus 1 over 5 factorial.
X to the 5th.
All right. Minus 1 over 7 factorial. Okay. However, still there's a problem. I'm not so sure if you guys understand what it means for sine x to be equal to x minus 1 over 3 factorial x cubed and so on and so on. I mean, can you get anything non-trivial out of this relationship? Can you get some additional knowledge that you wouldn't have access to just by knowing this? Does it tell you anything?
Shows us a pattern.
Huh?
Shows us a pattern.
No, that's not the point. Yes?
You can solve for any value of sine.
You can solve for any value. Elaborate, please.
So if you had sine x equal, let's say, 2,
Right.
then you could plug x into 2 and you would find the right value of sine.
That is exactly right. Okay, so if you want sine of 2, you just plug in 2 here and you evaluate that. Okay? All right. So suppose you're trapped in an island. Okay, or actually, I took you, right, and then put you in some cage and then put in the helicopter and dropped on an island, right?
Yeah.
Okay. And I give you a mission. You have to recreate all the technology of the mankind. Okay? And my suggestion is start with the table for the trigonometry. Okay, so give me the sine cosine tables. So basically what I'm asking you to do is, here's the angle theta, say 0 degrees, 1 degrees, 2 degrees, and so on and so on. And I want the sine theta value. Okay? Well, sine of 0 is 0, hopefully you remember that. But how would you do sine of 1 degrees? Any ideas? What should you plug in here? No, you don't plug in 1. Be careful. Yes?
You plug in the radian value.
Okay, what's the radian value of 1 degrees?
It would be
Pi over 180, yes. So you have to... Oh, we'll just pi over 180 radians. And by the way, this is only true for radians. For degrees, it doesn't work, okay? So this is only true for radians, so we do this. And if you actually put that in there, you get, what, pi over 180 minus 1 over 3 factorial. Let's see, pi over 180 cubed plus 1 over 5 factorial. Well, 1 over 3 factorial is 6. 1 over 5 factorial is 120. And think about it this way. Pi is about 3. 3 over 180 is 60. 60 cubed is 216,000. And there's another 6 times to it, so that's like 1.3 million or something. So this is one out of 1.3 million. Okay. Now if that's the case, think about the following. Let's say I give you the mission to complete this table with 4 decimal places. That's reasonable, right? So 0 point something, 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 something. 4 decimals, okay? But you already see that this is like being 1 out of 1.2 million. That's going to be less than the 4th digit, so we can just ignore that, okay? We can ignore this, we can ignore this, and everything else are just too small to matter, okay? So you just have to calculate this, okay? And let's say we actually do it. So what is pi? It's about 1.16. No, that's not. I was thinking of a square root of 2 for some reason. Okay, sorry. 3.1416. You take that and you divide it by 180. And, well, 0.01 gives you 180. Right? No, let's see. 0.001. Is that right? No, let's see.
You're right.
Yeah, 100. So 1.180 times 0.01 gives you 1.80, right? Okay, so you subtract, and that gives you 4 and 3, 1.34, 1. And then for this, you probably need about 7. 7 times 0 is 0, 7 times 8 is 56, 7 times 1 is 7, 7 plus 5 is 1.260, subtract. So that's about 0.0816. And about 4 would give you 720, and you're going to get some remainder. Okay? So you get this as the value that goes into this table. Can someone calculate the sine of 1 degree using degree mode? Don't put your calculator in radian mode. What do you get? What's the actual value?
0.17452.
0.0174
52
to something. Right. Yeah. So, look, we did it. Okay? Yeah.
That's 1 degree.
That's 1 degree, and then you have to do the other ones for, and then the degrees go up, then you'll have, this will start getting involved, and then it gets harder after this. But it's something that you can do, right? Okay. So let me ask a similar question. Again, you're still trapped, and you finish your trig table. And I say, no, you're not off, you're not going home yet. You have to tell me what E is, right? How would you get that?
Do you know what E is, or do you not know what E is on the island?
Value of E, what would you get?
It's like 2.14.
Okay, but how would you calculate it?
I would take minus 1 over.
You have it in front of you, right? What do?
You E to the 0.
Either one.
E to the 1. Yeah, E is E to the 1. So you plug in 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, which is 6, 1 over 24 plus 1 over 120, something. This is 2.5. This is 0.1666. This is like 0.041 or something. Then this it gets harder, so let's just do this. And then this is 2.6666, and then 1 is added, so it'll be 2.704 or something. Okay. Now the actual value of E is 2.7182818. So, I mean, if we added more terms, it'll be better, right? Okay. So that's how you do this. Okay, so if you're convinced that this equal really means equal, that's my first point. Now here's the next question I also think a lot of you don't know. How do you get these numbers though? How do you know that sine x is specifically the one with 1 here, 1 over 3 factorial minus, and then how would you get these numbers? Okay. Here's how you do it. You start by assuming that sine x is a0 plus a1x plus a2x plus a3x, a2x squared, a3x cubed, a4x to the 4th plus da. And we're trying to find the unknown coefficients a0, a1, a2, a3, and a4, right? Now, how would you get a0? Any ideas? How do you get this?
That would just be 0 here,
Why?
because any term to the 0 is 0. And
No.
subscript.
You substitute x as
0.
0. You plug in x equal to 0. So if you plug in 0 here, you get sine of 0, which is, by the way, 0. This is 0. This is a0. But everything here, you plug in 0, you get zeros, right? So you get zeros everywhere. Sine of 0 is 0, so you get 0 equals to a0. And that's it. You get a0. 0 is 0. Then trying to find a1 is completely different. How would you find a1?
Plug in 1.
nice idea, but it doesn't work. Once you plug in 1, all of these survive, and you can't come up with a nice way to just get A1 by itself, okay?
Derivative?
You take the derivative. Who said that? Who said that? Oh, pretty good. All right.
No, it wasn't
So
me.
you take the derivative, both sides, and you get cosine of x. That goes away, and you get A1 plus 2A2x plus 3A3x squared plus 4A4x cubed. Now what do? Plug in 0 again. Okay? So you get cosine 0, which is 1. A1.
Oh.
Everything else disappears, so you get A1 as 1. So I got this result. A0 is 0, A1 is 1. So you don't see any constant terms. It's 1 times x, right? Okay. Now how would you get A2? Differentiate again. Or 3 times 2. 4 times 3, A4. Plug in 0, and you get this as 0 equals to 2A2. You get A2 as 0. Differentiate again, and this time there's something, right? What happens there? That's 3 times 2 times A3, and then plus something else, right? You plug in 0, you get negative 1 equals to 3 times 2 times A3. So you get negative 1 over 3 factorial, because what's the factorial? It's 3 times 2 times 1, right? That's exactly the same as 3 times 2. So you get this. Okay. Now, once you see this, you see that the reason that you have this pattern is like every odd times you differentiate, every even times you differentiate, you get the signs and then you get 0. Okay, and only the odd terms survive because odd number of differentiation gives you the cosine, either the plus or minus. So you get alternating signs, and every time you differentiate, the numbers on the top comes down, and that's why you get these factorials there. Okay? So you see how this thing works? Okay. All right. Now, I really need every one of you to know by heart these two, because that's like basic knowledge for everybody, okay? Every engineer should know these, right? Okay, so differentiate sine x will give you the value of the cosine x's Taylor series, so that you get that for free. If you just memorize these two, then differentiating this gives you x differentiates to 1. Now, if you have 1 over 3 factorial x cubed, then if you differentiate this is 3 times 2 times 1. And this gives you 3x squared, and 3 cancels, and you end up with 1 over 2 factorial x squared. Okay. Same thing happens with the 1 over 5 factorial x to the 5th. If you differentiate this will be 1 over 5, 4, 3, 2, 1. 5 times x to the 4th. These cancel, and you end up with 1 over 4 factorial x to the 4th. So once you see this pattern, then you can now see that the derivative of these will be just the same kind of format. It's factorial down here, some power, but with one less. Okay? And then another thing I want to talk about here is that, in fact, the Euler identity that e to the ix is cosine x plus I sine x is obtained from here. So you just take this, replace x by ix, and you get 1 plus ix plus 1 over 2 factorial. Well, I squared is negative 1, so it would be negative x squared. And I cubed is negative I, so it would be 1 over 3 factorial negative I x cubed. And then I to the 4th is just 1, so you get 1 over 4 factorial x to the 4 back again. And let's just, the next one is x to the 5th, but that's going to come up with the I here. And if you just, so it continues forever. And if you just collect the real part, which is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth plus da da da, plus if you collect the ones with I in there, if you factor the I out, this will be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. And you can see that this one is indeed the power series for the cosine, right? And this is the power series for the sine. And therefore, you have proved the Euler identity. In case you didn't know where this identity came from, it's actually proved by using the Taylor series, right? Okay, so hopefully you will be convinced that knowing the power series means you know the function. That's what I'm getting at. Okay, so again, let me repeat this. If you know the power series, then you would know the value of the function for some values just by calculating it, right? And if you think about it, when can you say you know a function? You can say that you know a function if you know its values, because what's a function after all? It's something that gives you an output when you feed an input, right? So if you know all the outputs of that function, that means you know the function, right? And having the power series allows you to know it, right? So that's what I want to say before we even try to solve this. So I want to find the solution of this differential equation as power series, because by reviewing the Taylor series that we've done before convinces us that in fact if you know the power series, you know the function. Agreed? Do you agree? All right. So now let's move on to do it. Okay. So we're going to start out by saying y is a0, again, unknown, okay? Because we have no idea what it would be, so just put y as a0 plus a1x plus a2x squared plus a3x cubed plus da da da. Let's just put one more. The more terms you have, it gives you a better idea of what's going on. Okay? Now we have to differentiate. This just goes away, but you get a1 here, 2a2x, 3a3x squared plus 4 times a4x cubed. And then you differentiate yet again, you get y double prime equals to nothing. That's 2a2 plus 3 times 2a3x. And you don't want to multiply them and write 6 because we're trying to find the pattern. To find the pattern, it's better to not do the multiplication, just leave it like this, because sometimes you can just say, write factorial for some of the things. It's not always useful, but it's a good habit to have. Right? And then when you differentiate this, 3 comes down and you get 4 times 3, a4 x squared plus da da da. And all of these get plugged into the left side. Right? Y double prime is replaced by this, y prime is replaced by this, and the resulting equation is, let's see what we get. I'll just write it this way. Okay, so you get 2a2 plus 3 times 2a3x plus 4 times 3 a4x squared plus da 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 plus, let's put plus, and then 2x times this, right? So I put 2x times a1 plus 2a2x plus 3a3 x squared plus 4a4 x cubed plus da da da. And then plus 4 times the original one, which is a0 plus a1x plus a2x squared, a3x cubed, plus a4x to the fourth plus da da da, equal to 0 on the right side. Okay. That's a lot of writing, right? And hopefully we don't want to do all this writing all the time. And we can actually make that happen by coming up with a more compact or smart way of writing these. Do you know any smarter way of writing these?
Sure.
Yeah. What's a smarter way of writing these things? Yeah, you use what's called the sigma notation, right? Summation notation with subscripts. Okay? So you can rewrite this as sum of an x to the n going from 0 through infinity. Just like that. And for this one, you can just differentiate this, so n comes down, right? So n comes down and you have n x to the, what power? N minus 1. And in fact, this does give you the correct terms in here. So for example, if NAN, and you see 4A4, 3A3, so these numbers match, 2A2, all of them match. So this is when n is 1 and 2 and 3 and 4. But there's one thing that you wouldn't notice if you just calculate it with this. If you actually wrote it down, you see that the very first term, which corresponds to n equals to 0, vanished away because that's a constant term, right? So here, instead of n starting from 0, it should start from 1. Okay. All right, how about this one? Well, you differentiate this again. So n minus 1 comes down. So you have n times n minus 1, an, x to the n minus 2, summation of, what should n start from? 2. 2. To infinity. Okay. And this is in fact what we are going to do from now on. Instead of writing all this, which is really time consuming, we'll use this compact notation to replace that. Okay? All the while, just knowing that it starts with n equals to 0, n equals to 1, n equals to 2, and so on and so on. However, you're going to see that if you just use this without paying attention to what's happening with the actual longhand, this is the shorthand, this is the longhand, then you'll lose track of your calculation. So it's very important for you to be able to go back and forth between the shorthand and the longhand. Okay? So let me explain what I mean by that. So let's say we actually plugged into the left side. Here's what we get. We get, let me write in green. We get sigma n equals to 2 to infinity n minus 1 an x to the n minus 2 plus 2x times sigma n from 1 through infinity nan n times an x to the n minus 1 plus 4 times sigma n from 0 through infinity of an x to the n equals to 0. So that's what you get. And you wouldn't know what to do, whereas if you actually looked at these, you would know exactly what to do with this 2x. What would you do with 2x here? You would distribute it, right? Of course, you're going to multiply it to everything in here. Here. And same with this 4. You would multiply them inside. And what it means here is that 2x goes inside to get multiplied to every term in here. 4 gets multiplied to every term in here. That's what's happening. All right? And in addition, if you multiplied x with x squared, what would you write? X cubed. So you would add 1 with 2 to write x cubed, right? So when you move this inside, you wouldn't write x times x to the n minus 1. You would multiply these two and write this x to the nth power. So here's the resulting thing if you simplify. Okay. So you get that. And once again, I'm not going to be writing this, but for next time we solve a similar question, we'll just start with this differential equation, write y as this, y prime as this, y double prime as this, plug everything in, and we'll just naturally move everything outside to inside, and simplify any powers of x when we need it. Okay? So you should feel that going from this to this should be almost automatic. Okay? You don't have to think that much. It should be almost automatic. Now, but then, what do we do next? Well, your goal is to make the left side into a power series. In other words, I want to organize this entire thing as the constant term plus something times x plus something times x squared plus something times x cubed, and so on and so on. Okay? So let's look at the constant term, meaning that it's x to the 0th power. Which one has x to the 0th power? So here, when do you get x to the 0th power?
N is equal to 2.
N is equal to 2. So you put n as 2, so you're going to get 2 times 1 times a2. Now how about here? When do you get a constant term?
N is equal to 0.
But does that happen? You start from n equals to 1, right? So this one doesn't have a constant term. Now if that's confusing, go back to the original one and see what happens. So you're multiplying 2x to it, right? So does this have a constant term? No, the lowest order term is 2a1x. It doesn't have a constant term. So this one is silent when n is equal to 0. Agreed? Okay. So it doesn't produce anything. But then here, when n is equal to 0, you get 4a0. Okay. So you get 4a0. Plus. Now let's look for the x to the 1st power. Okay. For what value of n would you get x to the 1st power? N equals to 3, and you get 3 times 2 times a3. So 3 times 2 is 6. So I can write down 6a3. For this one, you would need n equals to 1. So 2 times 1 times a1. How about here? 4a1. Right? So you have 2a1 plus 4a1. Add them together, what do you get?
6a1.
6a1. Good. All right. Since we've done enough terms together, I want you to take your time to figure out what goes in here, inside x squared. Okay. So everyone get to work. Figure out what terms would have x squared in them and combine them in this format. And you have to figure out what goes in here. Okay. So do the work right now. It's very important that you understand this, because if you don't, then you wouldn't be able to understand what we do afterwards. When I give you time to work things, I ask you to be able to talk to one another. Okay, so if you have no idea, please ask around.
I don't know how we got the 6A1.
How'd you get
The 6A1.
Yeah, so
Huh?
that's the constant. So 6a1.
That's because for x to the first power, you would need n equals to 1.
Yes.
N equals to 1.
Oh, so you okay.
So if I put 1 here, 1 here, 1 here, this will be 2a1. That's 4a1. Adding the 2 gives you 6a1.
Okay.
Times x to the first power. That's great. You got it correct. You know, let me walk around. See if you got it right.
So I'm really getting all the beginning shit. So basically what you're trying to do is you're trying to find the value that you see your x squared here. So you're trying to find the value of 10 to get that to be x squared. So you see our three values here. These are representing our three terms in brown. So you got n over n minus 1, and then an x to the n minus 2. So that's x n minus 2, right? Yes. How do we make that an x squared? What's that value n power top? Alright, so this is x. So yeah, we look for x squared right here, right? Last one we looked for just x. Now we look for x squared. So it says x n minus 2. Running the x.
Because the first one cancels out. So
Can I go up there and point, or is that the So
how do you get x to the n minus 2?
x n minus 2. So what do we need to set
So it'll be
that x
so it'll be
any base course now? Is the x squared is
I'm asking you for this part. So the one that has x squared.
Right.
So the first one,
we plug in all terms are going to be equal, so that x squared in the end is all going to be on the outside, right? So we're just like, so basically we're factoring. So now we want to do basically all we got to do is plug in 4 for n in that first step. So it's going to be 4 open parentheses 4 minus 1, which is 12, and then a subscript whatever you put it on top for n. So these a subscript. So it's going to be 12a subscript 4.
Because they're technically
Just like that. Do you get why that is though? Now, look, for that term though, because now that we put in that 4, it's going to be 12a subscript 4, and then our x squared, which is the x n minus 2 is that's our fact. So that's how we set that term in. So now try with the middle. What did you need for the middle?
N is equal to 4.
2, yeah.
Where did you get 12a? So the first one squared 2, and you get x to the n minus 2 and x squared.
Okay, looks like most of you figured it out. Now, I want to point out that the reason that you're having such a hard time is because you're working with the shorthand. Okay, trying to decipher a shorthand is always harder than working with the longhand, whereas longhand takes too much time to write, right? But since we have the longhand in front of us, why not use this one? So let's see. Which one has x squared? This one has x squared. That's 4 times 3, which is 12a4, right? So it must be 12a4 there. And then here, there's x squared, but that's not the one we want because there's 2x being multiplied, right? It's actually 2x times 2a2x that gives you x squared. So 2 times 2a2, what's that? That's 4a2, right? But then there's another one, 4 times a2x squared also, right? So 4a2 plus 4a2 gives you 8a2x squared, so it's going to give you 8a2. Okay? But, you know, you can get it from here just by figuring out what n should be. So to get x squared, you need n to be 4. So it's 4 times 3 times 8, 4, so which is 12a4. For this to be x squared, you need n to be 2, so it's 2 times 8, 2. So it's 4a2. This one again, n has to be 2. There's 4a2. 4a2 plus 4a2 gives you 8a2. And that's how you get this. Okay. Now, you eventually want to come up with a pattern. And in order to get a pattern, let's just say we want to know what's in front of x to the kth power. Now, to get the x to the kth power, here, what should n be? N has to be k plus 2, right? If n is k plus 2 minus 2 will give you x to the kth power, as we want, right? And that would make this as k plus 2 times,
K plus 2 minus 1.
which is k plus 1, right? K plus 2 times k plus 1 times a of
K.
k
plus
plus 2.
Plus 2 starting.
So it's k plus 2 times k plus 1 times a k plus 2. I guess I need more room here. Okay, and then here, I just need n to be k. So I have 2k ak and 4ak. Combine them, I get 2k plus, sorry, should be 2k plus 4 ak plus da da da. And this has to equal to 0. Okay, so it looks like we did a lot of things, but if you think about it, it's a very simple process. All you do is you just plug this into the left side and organize in parts of x. That's all we did. Yes?
So Professor, like, now that we're here and we understand this, it's starting to look kind of like what would you, how would we solve for like k or something?
Yeah, we haven't gone to that yet. Okay, so at this point, let's stop and think again. Okay. Now, do you see that the left side is again a power series? Okay. What's a power series? Power series is it's a polynomial that's infinite degree, right? So it's some constant plus some constant times x plus some constant times x squared plus some constant times x cubed and so on and so on. This indeed is a power series because that's a constant, right? There's some constant times x, some constant times x squared. The next will be some constant times x cubed, and so on and so on. And you want this to equal to 0. And remember, in differential equations, when you say equal sign, what does that mean? It means that the two sides must be equal as functions. In other words, I'm trying to look at the power series of 0. So here's a question. What's the Taylor series of 0? Does anyone know?
0.
Huh?
Just be 0.
It will just be 0. Right? See, 0, if you think about the Taylor series, if you write this as A0 plus A1, let's just write it as B0, B1, not to confuse with that one. If you did this and you plug in 0 both sides, you get B is equal to 0, and you differentiate both sides and plug in 0 again, you get B1 as 0. You keep differentiating, plugging in 0, and you get all of these coefficients 0, right? So using the same procedure, we see that the entire thing is just 0 plus 0x plus 0x squared, so on, so on, so on. And if you apply that to this, which we know, what's our conclusion? We must have, for these two sides to be equal to each other, what should this equal to?
0.
This one.
0.
This one.
0.
And so on and so on, right? So we have infinitely many equations to solve. Okay. All right. So that gives us infinitely many equations to solve. 6a3 plus 6a1 has to be 0. 12a4 plus 8a2 has to be 0. Okay, and then, now at this moment, some people would just give up, right? This is like infinitely many unknowns with infinitely many equations. You've never done that. But it's doable. Like, just think about this as an equation for A2. Why don't you think of it as an equation for A0? I'll explain later, okay? But let's just say, just pretend for a moment that A0, A1 are the known things, and you just want to find A2, you want to find A3, and A4, and so on. Okay? So first of all, this one. What is A2? A2 would be, you move this to the other side and divide by 2. What do you get? Negative 2, A0. Now this one, if you move this to the other side and divide by 6, you get A3 as negative A1. Now for this one, if you move this to the other side and divide by 12, well, that gives us a fraction. So A4 would be negative 8 over 12 A2. Oh, but wait, it doesn't end there because A2 is negative 2A0, right? So you can further calculate this as, well, the top and bottom can be divided by 4, so it's negative 2 over 3 times A2 is negative 2A0, so you end up with positive 4 over 3A0. So that's what you get. And then you can keep going on, but doing it over and over again would be like too much of the same thing. You probably want to have some pattern, right? And that's why I put it here. Okay. So what we can do is, now let me erase this one because we're not going to be using this anymore. Actually, let me erase this much. And let me continue our calculation. See, this is true for all k. And it doesn't matter if you use k or n. So let me just replace all the k's by n. So I'm just going to write down that as, in general, n plus 2 times n plus 1 times a n plus 2 plus 2n plus 4 an has to equal to 0. And this actually is true for n starting from, well, it's even true for here, but this is somewhat different from the other ones because if you think about how we got this one, when we did this, we realized that this one's silent. The middle one is silent, right? So although it's actually true for n equals to 0 as well, just by coincidence, but in general, when you write a generic term, it's not true from the beginning. It's after some number n where it starts to follow a pattern. See, starting from here, they all follow a pattern because all of these terms, we get something from it, and they individually follow a pattern, right? So this one here is true for n 1 or greater. And we can solve this for an plus 2 by first subtracting this to the other side and factoring the 2 out. And then you divide and you get an plus 2. Well, n plus 2 can cancel. And you end up with negative 2 over n plus 1 an. Okay. So we get this relation, and this relation is what we call a recurrence relation. And it's a nice one to have because once you have the recurrence relation, you don't have to do this. You can just use this one. Okay? So for example, I got up to A4. Let's find A5. Well, that's when n is 3, right? So you put n equals to 3, 3, 3. So you get negative 2 over 3 plus 1, which is 4, A3. And that reduces as negative 1/2. And what is A3? A3 is negative A1. So that gives you positive A1, positive 1/2 A1. Okay? And you can see that you're able to use this over and over again to get A6, A7, A8, and so on and so on. Okay? So we can do this for a long, long time. All right. Now let's try to gather what we have so far and see what we have. So this was our initial assumption, right? We're trying to find y as a power series. And we don't know what A0 is. We don't know what A1 is. I do know what A2, A3, A4 are. Even A5. Okay? We got them. Okay? So let's actually put them in there. So A0 is A0, I have no idea. A1 is A1. However, you see that A2 is negative 2A0. So I can put negative 2A0 x squared. Then A3x cubed, but A3 is what? A3 is negative A1, so I put negative A1 x cubed. And then A4 is 4/3 A0 x to the 4th. And then the next one is 1/2 A1 x to the 5th. And then plus so on and so on. That's what we get. And we still don't know what A0 and A1 are. But let's try to do this. I see that some terms have A0 in there, some terms have A1 in there. So let's try to sort them out. So if I just select the ones with A0 in there, I get A0 times 1 minus 2x squared plus 4/3 x to the 4th plus da da da. Plus A1, if I collect the ones with A1, there's the x minus x cubed and plus 1/2 x to the 5th plus da da da. And if you needed more terms, you can calculate this more and get more terms, right? And I mean, even just with these much, you kind of know what this function is for a small interval, say 0 to 0.1. When x is 0.1, this is a small value, so you would end up knowing the output of that function to a pretty high precision, right? But still, some of you might be uncomfortable of not being able to know what A0 and A1 are. But in fact, it's a good thing for us. Why?
Oh, I was gonna ask a question.
Yeah.
So, how would when we're asked to solve something like this on an exam,
Yeah.
what will we be asked? Like,
Oh, okay, that's a good question. So the question is, when a question like this, and in fact, it is really scary. So you would see this as an exam question, right? And then you're asked to solve this within, say, 15 minutes. And you would have like 2 questions like this in the next exam. Okay? So it'll be pretty fun. Okay?
15 minutes?
Yeah, 15 minutes per question. Yeah. I took 40 minutes while explaining, but if you forget the explanation, you should be able to finish this in 15 minutes.
Do you have to solve it straight through like you did?
Yeah. This should be the answer. Right? Okay. Now, however, what am I looking for? Well, in some questions I might ask, find the recurrence relation. In that case, this is all you have. You just, when you say recurrence relation, you better have that n 1 or greater, or something. Recurrence relation should always have the condition for when it's valid. Okay. So this will be an answer. So if it's like a 20-point question or 25-point question, then this will be already 10 points. Yeah. And then you would find the answer to usually 5 non-zero terms. So you would start from here and then somewhere here. You can go more, but that's what I ask usually. Okay? 5 non-zero terms. All right, but back to my question. We still don't know A0 and A1, and I'm claiming it's a good thing. Why? Why is that a good thing?
You can use any coefficients.
It can be any coefficient. Why do I call them? You have a second order differential equation, and you want a general solution.
Constants.
The constants, coefficients. Okay, the correct term I was using is free parameters. Okay, so second order differential equation should have how many free parameters? 2. I see 1 and I see 2. In fact, you can think of these as separate solutions of the original differential equation, and you're just merely doing this. C1 times this, and C2 times that. Right? So in other words, A0 and A1 are taking the roles of C1 and C2. Okay? So in fact, this is all the solutions. We found all the solutions of this, and if I was given some initial conditions, say y of 0 is 1 and y prime of 0 is 3 or something like that, then that's going to give me the exact values of a0 and a1, and you would actually solve it, okay, just by doing this. Okay? So I'm trying to convince you that indeed this is the general solution that we want, and we've solved it. Because we found its power series. Of course, you know, a better thing would be to actually figure out the pattern of the coefficients, and you can sometimes you can write down this pattern as sum of something as a sigma notation. That'll be like perfect. Okay.
So that'll give us like full points on the.
If you are able to write down the full answer using sigma notation, yeah, I would give you like 10 points extra credit if you can do that. Yeah, that'll be like amazing. Yeah. But for my class, I just ask for people to be able to terminate at like 5 non-zero terms. Okay, and that's what we're doing. All right.